Hey. All right, I see we emptied out after the keynote. That's about what I expected. But that, I'm going to take on faith then that everybody who's here in the room has a distinct interest in getting better at writing good Yara rules. So we're going to go deep. A little bit of this we're going to go fast. But hopefully this will be fun and useful for those of you that are interested in the topic of writing good Yara rules, emphasis on good. The original title of this talk was the Derek Zoolander Center for Analysts Who Can't Write Rules So Good, but they told me that's too long for the bulletin and no one would get the joke. Apparently they were right, that's fine. For those of you that are interested in playing along and want to do Yara things while we do Yara things, there's a GitHub repo out there. I just put it up this morning. So go out to P. Melson, B-Sides Augusta 2022. And you can go ahead and clone that repo. It has a bunch of sample rules that I'm going to be going through in the talk. There's also a file out there, a 7-zip file with a password. If you've been doing this for a minute and you know the password, then you also understand the value of that proceed with caution sign. I'm not going to publicly admit to violating any GitHub terms of service. It'll be up to them to figure out what's in that file. But we might talk about it at the end. So that's the other thing, by the way. Stick around, because I think the best part is the live demo at the end, where you're going to help me write a Yara rule for malware that's never been seen before. So, but first, a little bit of grounding. What's Yara? Yara is an open source tool developed by VirusTotal. They call it the pattern matching Swiss Army knife. But what it really is a rule engine that provides a human readable rule language, a mnemonic rule language. And it supports sort of 3 key characteristics. So user defined patterns, strings, bytes, regex. We'll get into all of that in a little bit. Parsers, they call them modules, but what they really are is file parsers that give you, sort of direct shortcuts to be able to interact with particular types of files and file types, and we'll play with some of those later. And then a Boolean logic engine, and that's really the magic in this, right? It's like grep and awk on steroids, because you can do kind of all the things with that logic engine and some of the things that they expose in the conditional part of the rule. So let's ground a little bit on Yara syntax. So this is an example rule. This rule doesn't really do anything. I wrote it specifically so that we could talk about rule structure. So you'll notice all rules begin with the verb rule, and then the name of the rule. That's how you declare a rule, and then open curly brace, and everything that happens next is the rule until the following closed curly brace, right? Fairly simple, kind of straightforward markup. And then there are sort of 3 sections. Meta is a section where you put your metadata, fairly simple. It's a key value kind of thing, right? So on the left is your key name, equal sign, and then whatever's in the double quotes is your value. You put whatever you want in there. This is completely free form, but there are some things to think about when you're writing rules that you should consider. Does anybody have a thought as to what the most important field in the meta section is? I'll give you a hint, it's not the first one. Ooh, hash is a good one. I like people that put hashes in their meta field, but that's not it. Description, right, absolutely. What does this do? The second most important field. Nope, not author, not hash. Date, exactly. When did you do this? What are you trying to do, and when did you do this? Because the difference between, if I'm looking for Yara rules to help me detect a particular piece of malware, a rule that was written 2 months ago is different than a rule that was written 6 years ago. Not to say that the 6-year-old rule doesn't necessarily have value, but it changes my assumptions about what I'm looking at, how effective it's going to be, and what I might need to do to be able to leverage it, right? So I do think author is sort of an important field, not just for the credit aspect of it, because frankly nobody ever has paid me for releasing Yara rules, but moreover because it gives the person who's looking at that rule down the road a touch point to come back to if they have questions. Another thing you'll notice, so the hashes, what's the most important thing about that hash if you're going to put it in the rule? Well, sure, okay, it's got to be accurate. No, but the most important thing is it's got to be on a public repo, right? That file needs to be on VirusTotal or abuse.ch or VX Underground. It's got to be somewhere people can get to it. If you put a hash value up there that no one can get to, you're a jerk. And I'm not going to name check any companies that do this on a regular basis, but there are a couple that like to release Yara rules with IOCs that no one has access to, and that's the most useless thing in the world, because I can't check your work, I can't validate what you're saying is actually true or not, and now you're gonna make me, at best case scenario, you're gonna make me burn a retro hunt to try and find something else so that I have a sample to work from, right? All right. So enough about meta. You can do all kinds of things with it, add tagging, categorization. I've seen our internal team has a whole standard for Yara rule headers that they leverage that makes it easy for them to index, cross-reference, actors and things like that, right? So you can put all kinds of data in them that that make them useful for whatever your internal ops are. But so those are some sort of standards. Strings. Fairly straightforward. It's just pieces of values that you want to be able to reference. These, you'll notice the names start with a $sign. It's variable name. And then whatever's in double quotes, or as you move down. So my first example is just a regular text string, a UTF-8 string. You can also, and you'll notice some of the lines have additional modifiers after them that indicate what type of string we're looking for. If you don't indicate something, it's the same as putting ASCII in there. So you can use ASCII to differentiate this is an ASCII string, but if you don't, that's the implication, the implied value. The next one is a wide string. So wide, sometimes also called long or UTF-16, it just means that when Yara looks at that, the compiler is going to insert a null between each of those characters before it begins its search. No case, fairly straightforward, case insensitive. I camel cased that just to emphasize that, but obviously the camel casing inside of a thing that I put no case in is sort of redundant and silly. Again, you wouldn't really do this in a real rule. Regex, regular expressions, PCRE-ish. I say ish because there are some things that happen with escaping characters in Yara regexes that make them a little different. But I would say, for the most part, it's PCRE compliant. You can do, I would say, 99% of the things you would want to do in a regex, and probably 100% of the things you should do in a regex. But so regular expression support, and then byte strings. And byte strings are fun because you can essentially, you have full access to the entire character set. And byte strings also have some cool features. They support, regex style alternates and wildcards and some of those things, which are super handy. So especially when you start getting into opcodes and things like that, byte strings are the way to go. And then conditions, I just put so you would never actually use, so any of them, so them refers to every string in the string block. So any of them would mean if any of these strings is present in the file, the condition becomes true, it returns a true. All of them means that every string listed has to appear at least once in order for the condition to be true. And obviously, if you're any good at Boolean logic, you know that this is stupid because any of them supersedes all of them. If any of them or all of them can be true, then it's just an any of them statement. But I did it mostly to show off the parentheses and the fact that you can chain conditions together with ors and ands. And we'll get into some more interesting versions of that later. And this is what it looks like when we run it. So our test file is hw.txt, says hello world. That rule we were just looking at is hw.yara, which is our hello world rule. Run it against it, you can see the match. The output you get is rule name followed by file name, and that's the default output. I also added the -s switch, which is like my favorite debugging switch. It just shows you all the string matches at position. So you can see we matched on everything but the UTF-16, the wide string in that rule because our file doesn't contain that value. Some interesting things to note. With the case insensitive match, we didn't get the value of the string, we got the value of the block from the file. And the same with the regular expression string, we didn't get the value of the regular expression output, we got the value that it matched on. Interestingly enough, with the bytes string, we still got the value that it matched on, but it gives it to us in hex format and not in text format. I'm assuming that's just a default to make processing the output easier, because obviously you can access non-ASCII values and non-escaped values in byte strings. But so interesting that it would output that way. But it's worth noting for those of you that don't speak hex that that is in fact the exact same hello world string that the other strings are matching on. Oh, and 0x0, that's the offset of the beginning of each of the matches. And that's a super, super handy feature when you're doing rule development, to know where in a file you can find the match strings that your rule is connecting on. All right, so a little more. This one is, this is Hello World Take 2. The point of this is really to demonstrate some of the more advanced functionality in the conditions block. So we'll just skip straight to that. So file size is an internal mnemonic. In this case, we're going to say any file. By the way, hello world hw.txt is exactly 12 bytes. So file size less than 13 is a condition. Any file over that, we're not going to match on. So we can start calling into the variables directly. So hello at position 0 and world in the range of 4 to file size. So file size just becomes a number. It's essentially an integer that is exactly the number of bytes that the file that is currently open in the rule is. But you can use it in a range. We could have said 4 to 100, 4 to 12, if we knew what it was going to be. But 4 to file size lets us access that. It just means end of file. Or hello world and, or hello and world, or all of. And then this is a cool example. I love doing this. You'll see some of this later, where I classify the strings. Like I'll give them like a grouping name, and then usually an underscore to separate the individual value, so that you can use the asterisks to call groups of things in a single item. So you can wildcard your variable names inside the conditions, and that's super handy too. And so here's an example of this one, and you'll see now with the output and the offsets, we get hello is at 0, but because hello and world are now 2 different string matches, you see the offset for world has moved to the 6th position in the file. Well, world was always at the 6th position, but the match starts at 6 now because it's a separate value. Okay, a little bit about modules. Like I said, we're going to start moving deep pretty quick. Modules are awesome. Highly recommend using them. They save you a bunch of time. Somebody spent a lot of time writing a module because it saved them time. So if it's going to save them time, it'll save you time. That top rule is an example of a DLL check. You'll notice there's no strings. It's just a single condition. We import PE, kind of Python style up top. So PE is the module name. And then that gives us access to all of the functionality within that module. And typically the way that you access that is in the conditions, and it'll begin with module name dot and then the capability. And you can have essentially subordinate functionality, right, where there's multi-layers of functions, each separated by a period. But in this case, is DLL open and close parens. So, and all this does is if a file is in fact a Windows portable executable dynamic loadable library, a DLL file, it will return true. It'll match on all DLLs. In order to do this without using the PE parser, you end up with this condition stack down here, and I'll walk you through kind of what we're testing for. So the first is we're going to look for the magic number. So everybody, or not everybody, but you probably know that Windows executables, the first 2 bytes are the capital M, capital Z, sometimes called 4D, 5A. In Yara, you're going to interact with integers inside of conditions as big endian. And you'll see this a little later. If you do it in strings, you do it in byte order. If you do it down in the conditions, you're doing this big endian. So what you have is uint 16. Declare an integer at a position. In this case, we're taking position 0, so the beginning of the file. Uint 16 says, give me an unsigned integer length of 16 bits, which is 2 bytes. Right, so the first 2 bytes of the file at position 0 equals big endian 5A 4D, which is 4D 5A, it's MZ, right? So just to walk through that to explain what that's doing, literally that first condition is just what are the first 2 bytes, are they MZ? The next one is looking at offset 3C, and if uint16 is looking for 2 bytes, uint32 must be looking for 4 bytes, right? Because 32 bits is 4 bytes. And again, it's big endian. So what really all that is that's the letters P and E, because that's how you declare a PE header, followed by 2 nulls. But again, big endian style, so 00, 00, 45, 50. And then the last piece is we're going to add an additional offset of 16 because 16 bytes off of the beginning of the PE header starts the PE header's characteristics section. And those 4 bytes at the characteristics section tell you what type of file it is, and if essentially if 20, if 32, decimal 32 is set, hex 20 is set in that position within those 4 bytes, that indicates that it's a DLL, right? And the whole point of showing you this is that in order to do this manually, you have to really, really understand at a deep level what the files do, how the layout, you actually have to go read that Microsoft link that I included there that gives you the full breakdown of how image file DLL gets set in the PE header flag. Or you can use the module and write that one line and never think about it again. All right, and just a proof of life, so DLL.Yara contains both of these rules in it. Run them over the same files and you'll see they both match. And I just ran that against my zoo, so these are just some loaded DLLs in the wild. All right, so let's talk a little bit about Yara use cases, right? That's syntax, that's how to use it. What can we do with Yara, right? And there's a variety of different use cases. I'm going to move through these fairly quickly, but I think it's worth understanding the 4 important use cases. You're going to wonder, why is this guy that has dedicated so much of his career to detection saying detection is not a use case? Because that's all Yara does. Yara is a true-false engine for matching. That's detection, done and done, right? Like it either matches or it doesn't. That's detection. So let's talk a little bit more specifically about the intent that you need to have authoring a file, especially when you're thinking about how to write detection. So identification rules. So an identification rule would be an example of a rule where you want to positively ID a file. Let's pick on malware, right? Like I definitely want to, I want this rule to say definitively that what I'm looking at is in fact a plugx sample or a Benitu sample or whatever the malware family is, right? And so the goals are going to be a really positive identification. I'm going to want to be confident that what I'm looking at is in fact the malware family I'm looking for. I also am going to want a really low false positive rate. The downside of that, though, means that I'm engineering for specificity. I'm going to include tool marks. I'm going to include metadata. I'm going to include functional code in those things that I'm looking for when I'm writing that rule. The downside is there's a chance for false negative rate. That rule is going to be a little bit brittle. It may also be easy to bypass. If I publish this rule, the author may go out and say, oh, he's similar to the talk that Tim Medine just gave on the Defender bypass that was hooking on Tavis Ormandy, which, by the way, I'm proud of myself for not coming on hot mic and just saying, yeah, well, defenders get to be lazy too, because if it works, it's not. If it works, it's not stupid. Tavis isn't on my list, but there are a handful of offensive tool authors who I absolutely have detection just for their name just occurring in a file, because it's always worth looking at. And bad guys don't strip out comments as often as they should. So anyway, but they might leverage that same information if you release a rule into the public stratosphere. They may go, oh, I can just change that value, and now your rule doesn't fire anymore. So. When I think about identification rules, I definitely want to focus on those functional artifacts and required code to reduce the likelihood of false negatives. You really want to hook into what those capabilities are so that in order to bypass a piece of detection, the author has to change not just the metadata and arbitrary values that don't mean anything that you're identifying. It's not that you shouldn't use those, but you shouldn't use only those, because if you can hook into functional code, well, Now they have to change how their tool works. And at the end of the day, if you can make an adversary have to change how their tool works every time you write detection, you're eventually going to exhaust their resources and win. Classification rules. So this is where we're looking for the existence of known values, right? We want to be able to say, with a high degree of confidence that this thing does a particular thing, right? So this file is an executable that loads a series of functions like maybe from WinSock 32 DLL that establish outbound junk socket connections with connect, right? That would be a really good one to have some detection for. Why? Because no modern application is using WinSock 232 for outbound socket connections. That's a terrible idea. We quit doing that in the early 2000s. But the functionality still exists, and you know who does it all the time? Cobalt Strike. And Meterpreter, and Sliver, and, right, like, so there's a, but that's just it, right? That's almost like a code TTP. Like, I don't want to say, I shouldn't have said TTP, but it's a code technique that isn't necessarily going to positively ID a thing, but if a thing does that thing, it's probably worth looking at. And so that's the goal of a classification rule. Obviously, you're going to run into some false positives because if you're capitalizing on the functional selection and the bad coding practices of your adversaries, who, by the way, most of your adversaries have really bad coding practices. If you're focusing on those things, eventually you're going to come across a developer who's not a criminal or a spy who also is bad and wrote a bad thing, and you're going to hook their stuff too. Oh well. And then, this is also where you start to run into performance trade-offs, right? Because one of the other things you want to do in this scenario is account for variables and variability. How many different ways could this thing happen? I'm going to walk away from some of the specific context I've seen in specific samples and try and broaden my horizons a little bit when I think about how I write this rule. The downside is that means the number of strings and the types of encoding and things like that I'm going to include in the rule are going to go up some. So that leads to the pro tip I have for writing this kind of rule. If your rule is more than 20 lines, it's probably not one rule. With the identification rules and hunting rules, go nuts. One, because you can sort of accept the you need the specificity for identification. When we get to hunting, with hunting you have more cycles, you can be more expensive. But for classification rules, especially if you do intend to use them for alerting purposes, it's important to keep them kind of tight and constrained, and it's better to build groups of rules or families of rules rather than one rule to rule them all. So hunting rules, distinguish anomalies or suspicious files. You want to match on suspicious content. You want it to be flexible. Potentially high false positive rates on things like this, and you'll never be done tuning these. The other piece of advice, and this is just let me show you one of my scars. This is why comments exist, because you'll deploy a hunting rule and it won't fire very often, and you'll forget about it, and then a year later it'll fire, and if you just kind of hack that one up and shot it off into the stratosphere, and you come back to it a year later, and man, what was I thinking? Right? Do future you a favor and comment your rules, especially your hunting rules. You should comment all of your rules anyway, but really, really with your hunting rules, there's no limit to the number of comment-free text. It doesn't have any performance impact. Just go nuts. Be like, well, I saw this thing, and I was thinking this thing, and I'm not really sure, but maybe this could work, or maybe that'll work. I'm not, right? Like, go nuts. And then finally, triage rules. These are my favorite, and they're the most undervalued use case for Yara. But the whole point of triage rules is, and this is the -S flag use case, right? We're going to use Yara to extract interesting things from files before we even start our analysis of the file, right? So the downside to triage rules, of course, is they're completely useless for alerting. You wouldn't put these out in the world, right? So I'll give you an example. I have one that's my go-to that I call extract indicators. It has some really tight regular expressions and a little bit of good logic for finding both encoded, obfuscated, and just plain URLs, and fully qualified domain names, and file paths in files, right? So if I'm looking at an executable file, if there's right, if there's PDB references or there's a URL, that's potentially really, really interesting info to have as you're getting ready to look at a file. And if I can get all of that in whatever context, and instead of having to spend 20, 30 minutes slicing it up in CyberChef or whatever, I can just run Yara over it. Yara just pukes out the things and tells me where they are in the file, gives me some hints where to get started. The downside, of course, is you would never, ever use that for detection, because how often is there a URL string somewhere in a Windows executable? You might think to yourself, well, only if it does HTTP. Nope, everything. Every signed binary everywhere has a URL in it, minimum. So nope, terrible for detection, never do that. All right, a little bit about Yara performance. So some performance concepts. I want to talk a little bit about anchoring. So some of these are really fancy, fun academic words. I'm going to break them down. Anchoring just means use a big string instead of a bunch of little strings. Why? Because the bigger string gives more context, more positionality. It reduces the likelihood of that value being misinterpreted. It also has some very real performance benefits. I'll talk a little bit about specifically how the Yara compiler deals with performance and how you can think about writing your rules to help there. But so anchoring just means use a big string and minimize the amount of kind of wildcards that you're using in those strings if you can, right? So for example, in the hello world example, using hello world as one string with the spaces and the punctuation is far better than hello and world, because those matches can happen in any order, any place in the file. Versus, hello world tells me this comes before this and is separated by this. That's super useful. Cardinality. Cardinality is a really fancy word. I recommend you learn it so that you sound smart, but it just means counting. The cardinality of a thing is the anticipated number of times that we will count it. So high cardinality means lots. Low cardinality means not lots. So anyway, we're looking for things that are anticipated to be of low cardinality, which means they shouldn't happen a lot of times in a given file, right? And I'll give you some examples of good and some examples of bad. Regex performance, use ranges. If you're writing Yara rules with ranges that start curly brace 1, curly brace, get out. You can do that for you on your local machine, never deploy that. Never ever deploy that, because that means literally every time it tries to match on that, it is trying to match from a single byte to the end of the file. The number of cycles and the amount of memory you're wasting is obscene. You're the hole in the ozone layer, okay? Wildcard, same thing, .star, please don't, because .star does the exact same thing if it's unbounded. And then use alternation sparingly. So for those of you that know regex, alternation, right, is parenthesis, value, pipe, value, parenthesis, right? And it means if any of those values exist in this position in the string, that's valid. It's okay to use that, and actually I highly recommend it, especially in the byte strings. That's a super handy feature to have. But keep in mind, if you have multiple alternates in a single regex, that's not a coefficient, right? That's an exponent to the number of strings that have to be pre-computed in order to do in order for your rule to run. So keep those to a minimum. And quite honestly, if you're looking at your regex and you've got one that like line wraps and has a bunch of alternates and different tokens and things, what you probably should have is a couple of smaller regular expressions and then work out the hard stuff in the conditions. And then finally, order of operations. You might think order of operations matters. Yara doesn't care about your order of operations. So a little bit about the Yara compiler, and credit where credit is due. So I will link it at the end, but all of this information comes from, it's a paper that Florian Roth wrote that's sitting out on GitHub. It is the paper on Yara performance and how it works. If you need to go deep on this, especially if you're going to be scanning tens of thousands of files or trying to do real-time Yara, highly recommend reading it, but I'll try and give you the high-level overview. So Yara does two things when it compiles your rule. It optimizes strings, and it does condition optimization. With strings optimization, there's this concept called atoms, where it will take a larger string. So let's say a long string with good anchoring. It'll take 3 or 4 byte chunks out of it. Now it's got its own algorithm as to which it will try and take, right? But like if you had a long string that on one end had a wide amount of variety and at the other end was like all A's, right? It's going to pick stuff where there's more variety, right? Where there's distance between the bytes. And then once it builds that list of atoms, it searches the entire length of the file from position 0 to the end of the file and creates an index of all those atomic matches. It doesn't matter what's in your condition statement. So you might think your condition statement that says, hey, if this isn't the first byte of the file, quit and go away. That seems like a good optimization strategy, but it's actually not for Yara, unfortunately. It's still good for you from an assurance perspective, but it doesn't make the rule faster doing it that way. And then finally, after it builds that index, it goes through and searches for each of the full string matches by expanding the strings, looking at wildcards and regular expressions. So that's how it optimizes the matches, right? It picks what it thinks are going to be some good byte chunks, comes up with an index, and then expands each of the searches locally within those positions so that it doesn't have to run your terrible regex over the entirety of the file. And then condition optimization, so it picks which checks it runs first. So simple logic, right? So this equals this is present, this is true. Imagine if you already, and this is why it does the simple test first, right? If you're just checking for the presence of a string, well, it already has the atoms and index that make up your string. If any of those don't exist in the indices that are referenced in your condition, then it can quit right then. It then moves on to expensive operations like math and comparative. So it'll do simple things like equal, and then eventually moves on to comparatives like greater than, less than, and then eventually other things like ranges. And then finally, it does module calls last. So that's the performance trick for modules, right? Is that modules vote last. If the other conditions aren't met, the module never runs. All right, so example of good rule, bad rule. So these two rules do the exact same thing. They detect a PE file, similar to the DLL rule I showed you earlier. So in this case, we have the good rule has a single string. This program cannot. You could do this program cannot be run in DOS mode, except I will tell you that there are more variations of this string than you would think out there in the wild. So my personal for hunting is I use his program can. That sounds silly, but you get some variation in casing and wording in DOS stub headers for whatever reason. Delphi does some weird stuff, things. Anyway, but it's a nice string, low degree of cardinality, good anchoring. And then we're not creating, and then we go directly to the byte comparisons for is it an MZ, are the first two bytes MZ, does it have a PE header, and then does this string exist? And we give it a particular position. The bad rule, we declare these as strings, so they all get searched first. Well, what do you think happens when we search for 2 bytes, right? It can't atomize it, so it's got to do a full string, full search for everything across that. We break those up, which means that we lose the context and positioning and ordering among those strings in the PE header, and then trying to do PE header in a range rather than being specific about where it should be based on offset. So interestingly enough, that uint 16 equals 5A 4D is significantly more performant than just declaring MZ and saying MZ at 0. Literally, logically identical, but from a performance standpoint, because Yara doesn't care about your conditions until it's done searching the file, you're running an expensive search before you get to the logic piece, right? So hence the optimization. So it's a little counterintuitive, but this is, trust me, the two rules perform very differently. So, but let's talk about a rule that performed even more differently. So Yara added support for XOR matching on strings, which is awesome if you've ever run into XOR as obfuscation. This is super handy to be able to do this kind of detection. This is actually a use case that I ran into not that long ago. And it was like, oh, well, I'll just look for, I'll go back and look over. So what I found was a .lnk file, right? A Windows shortcut file that contained within it some PowerShell that actually took the file at a particular position and XOR'd it by a single byte key and extracted a whole ass rat like onto disk and then ran the rat, which is, that's a nice trick if you can get it. I had seen the Cobalt Strike version of that where the payload's actually in the base64 PowerShell script, but those are pretty easy to detect because it's base64 in a link file. This was a workaround for it, which I thought was pretty novel, but thought, hey, well, how do I go about this, right? Because I don't necessarily have a file structure to work from, so I'm just going to look for some header artifacts. And I got yelled at by Yara, as you can see there at the bottom. So this particular link file is 88K. It's a pretty small file. In fact, I'll be specific. It was 89,878 bytes, right? That's a little file. How many times do you think that the XOR extrapolation of MZ appeared in that file? It was a couple times. So if you guessed that it was 526 matches in an 89K file, then you must have downloaded the GitHub repo at the beginning and be playing at home. But yeah, 1.2% of the file matches. Why? Well, because M and Z, capital M, capital Z, they're at a distance of 13. And basically, by XOR encoding them by all 256 potential values, you essentially end up with every 2-byte sequence that has an exact distance of 13 matches, and it happens a lot. We'll just say a lot. So really terrible performance, bad rule. So if we were to go back and revisit this, like, how would you tune this rule? The answer's pretty easy. We just take that out. We leave the lower cardinality string in that only had one hit, and we take this out. A better solution is to do this. So this is my pro tip on XOR. If you're going to be using Yara for XOR, they had this really cool feature where you actually get to define keys and key ranges. So you can say XOR, but just give the specific key, or you can actually give it a range. And so in this case, I'm intentionally excluding 2 XOR values. The first one is 0. Anybody know why we exclude XOR 0? If you XOR a value by 0, it's just the value. It's like multiplying by 1, right? And the other one, and this one, this is just me showing you another scar. The other one is hexadecimal 20, which is decimal 32. And if you XOR an ASCII character, an alphabetic character, by XOR hex 20, you will get the case alternate. So you will take lowercase characters and make them uppercase, and uppercase characters make them lowercase. There's probably a PhD level computer science history paper on how we got there, like going all the way back to like ancient Greece, and then decisions made, by ANSI and things like that when we decided what characters were what byte values. But anyway. So those are my tips, though. Don't use either of those. If you're looking for obfuscation, avoid using those 2 particular XOR keys. All right, cool. We're doing all right on time. So now it's about to get weird. We're going to write a Yara rule today. Well, first let me introduce you to my guy. So this is JWoww. I think the appropriate Brazilian pronunciation is João, which I think is like an equivalent to John. But I've been stalking this guy's malware for a few years now, so he's JWoww. This is an old picture of him. It's the only one I've been able to find. But he's got a YouTube channel and some other stuff. He's you can find him on HF and a few other places. And this summer, he started playing with a new dropper that he wrote in .NET. And I didn't have any Yara for it. I hadn't seen it before. And I knew that I had to write, I was working on this presentation on Yara rules anyway for B-Sides Augusta, and I was like, you know what, YOLO, right? Like, why not write a Yara rule together? And for no other reason than to kind of walk you through how I approach this process, which may come as a disappointment to some of you because it's not as hard or as cool as it sounds. But, so let me see. Can you all see my VM? Nice. All right. So these are 8 samples that I pulled. You're probably like, well, how are you attributing to this guy? I'm going to just ask that you trust me. If you want to see receipts later, I'll walk you through it. But I can tie most of this stuff back to his username in a few different places. And he hasn't done a video on this one yet. So the fun thing is we're actually going to get to see a couple of dev versions that he's been deploying. In fact, the other implant that this drops is named Teste, which is just the Portuguese for test, right? And he's got a dummy implant out there that he's been deploying all over the place just to get his attack chain working. So that's kind of fun, right? It's neat to watch an adversary work live in the wild. So first, what do we know about these samples? I just hit them with file. And so can everybody read that okay, or is it too small? All right. See if I can. So anyway, if you're not able to see, it's they're all DLLs. So these are drop DLLs. They're coming in through. It's an ugly combination. Windows scripting host to PowerShell back to Windows scripting host dropper to run 32 DLL or run DLL 32.exe. Sorry. So anyway. But these are roughly the same size and have a similar origin. So the first thing that I like to do when I'm looking at these, especially now that I know, okay, it's a DLL and it's .NET. So something that I already know about .NET is in a lot of cases there's a strings object that and a bunch of different like resource blocks in the .NET directory, and when it stores strings, it stores them as wide strings. So the first thing we'll do is just extract all the wide strings. And in Linux, that's -el, so Linux, it's long strings as opposed to wide strings, but it means the same thing. All the files, we'll just sort them, and then we'll use unique to get a count, and then we'll sort the output from unique in reverse numerical order, and pipe to less. And so what we get is this list of strings. And you can see, so the first thing we know is if the count on these strings is less than 8, because we have 8 samples, then those strings don't appear in all the files, so we can exclude them from detection. Doesn't mean that they're not useful for later analysis and intelligence purposes, but they're not going to make good detection because they aren't universal. But everything that's got an 8 or better next to it is fair game. So now we're going to look around and see, I don't know how many of you looked at the tail end of .NET binaries before, but you'll see a lot of things you recognize in there, like legal trademarks, legal copyright, internal name, right? That's all just stuff Visual Studio does for you when you name a project, if you decide to. So that just lets you know that he's using Visual Studio. It's no surprise, but tons of stuff is going to match on those. So we're really only interested in a handful of strings here that might be unique. So the first one at the top up there, that's odd that that sort of random looking string would occur 32 times, which would tell you there's probably 4 copies in every file of that. So that's a good one. We'll grab that string. There's a couple others over there. I mean, there's the name of the DLL and then resources. So that's interesting. We'll grab those. And kind of looking around, I'm not seeing anything else in the 8 count that's necessarily super useful there. So let's switch over to the ASCII strings, or in this case, S for short strings. So you see all I'm doing is just changing the E to an L, and now we're going to get out the non-null padded string values. There's quite a few more of these, but again, we're only looking for ones that have 8 or more. 15 is always scary because that would tell you that there's 2 in every file except one that only has 1. But in those cases, in this case, those aren't particularly great strings either. The dispose instance, create instance. We can see pad, and a few other things. But we see we get a repeat of this YIPP-HB, so we'll take that. That's interesting. we'll just mark these up here. Another interesting one that kind of pops out to me is this version number right here. So we'll steal that one. Oops. What am I doing wrong here? I'm failing at copy paste. That's doesn't bode well. Copy. All right. So, and as we look around, you know, I see a bunch of other kind of code-related stuff that's potentially interesting. We do see that, you know, further down, we see that PPPS XT QIU does repeat. So maybe we grab that one as well. That's interesting, and it shows up in both cases. We can see, let's see, what else have we got? There's quite a few. Oh, there's some interesting stuff down here. Kill, JSKLO. Hide module attribute name, that's potentially interesting, especially if it's actually being used. Instance is probably not super useful in this case. Ooh, we've got some debugger modes, debuggable attributes. And by the way, if you see things here that you think are potentially interesting, you know, as we're kind of scrolling through some of these, don't hesitate to shout them out. Okay. Ooh, write process memory, that's a good one. But there's only 7 of those. Oh, but there we go, here we go. Get process by ID, that's maybe helpful. All right, well, that's a good start. So what we've done, though, is just go through and look for a list of strings that kind of exist across, or what probably exist across most of the files. The next thing, though, before we start writing a rule is, let's get an idea of what the context of some of these things is. So I'm going to flip over to my handy Flare VM machine where I've got dnspy loaded. You know, so it's a live demo, but it's not totally uncooked. There are two different samples from that folder set shown here. So you can see one up top and one down below. And you'll notice there's a little bit of a difference between the two, where one of them has pretty like crazy looking like you know, resource names there. And the reason for that is that our adversary, our actor, has run ConfuserX over this, which is a packer. And so it's gone through and taken a bunch of the variable names and so on and renamed them to kind of ridiculous, unpredictable things. And we could anticipate that if he's going to rerun ConfuserX over this file every time he launches, you know, every time he creates a new build, these names are going to be, you know, changed each time, right? So what's actually useful here is we get a sense of which code artifacts, you know, down in the unobfuscated version, right, where we can come in here and actually look at the class and see, you know, this is pretty much going to, you know, this will be fairly close to the code as the actor wrote it. But as you can see in the upper example, right, a lot of the useful you know, code names and strings have been blown away, which is why they don't exist in all of the files. So the important thing then is to start looking at what are those pieces of the file that do kind of persist and repeat, right? So we'll start by looking at the actual module itself. So that yippphb.dll, that's what he named the module in the Visual Studio project. And we can flip around and see a few things here. We do see module type is DLL, so it sort of validates what we were seeing earlier. Oh, we had seen that string before. That is, in fact, the .NET version string. So we can actually use that in constructing the file. And Yara's .NET module will let us actually key in on that. So it isn't just the presence of that string, but we can actually specify how that string is being used, which is potentially helpful. A few other things we can look around at. Well, again, we know it's a DLL. Oh, let's see, what else? Well, we can get down into this class here. So that POL-WKB is a, and we can poke around in here, interfaces, generic params. Here we go. Edit the method. It's not setting a lot of custom attributes on these things. I'll show you characteristics while we're standing here. So you can see it there about midway down the screen on the left. And that's what the hex bytes look like, that 2000 or 2000 in hex. In this case, it's 2022, but that 20 still indicates it's DLL. And then another thing that we can do, Ctrl+Shift+K, there's my keyword search. Here. There we go. Oops. All right. So a couple of the things that we can compare as we're looking through. One thing you'll notice in the obfuscated version of the code is there, so in the deobfuscated version of the code, right, we can see that he's, because it's VB, he's manually calling DLL import rather than using native .NET inclusion for these functions. So he's got to call the function, got to call the DLL and the function name by name here using DLL import, which is an interesting artifact because when he goes to run his obfuscator on this, we also see that he has to leave those values alone, right? Because if you obfuscate those particular values, now it's worth noting, right? Like, and he'll probably watch this later online and then fix this, and I guess I just accept that that's the cat and mouse game we're playing here in the name of education. But the way that he's implemented this now, we can take the create process and kernel 32 DLL strings, use those as pairs, and basically call out all the functions that he wants to use in here. And some of these are pretty useful, right? I mean, it's a dropper, so read process memory, write process memory, unmap view a section, virtual alloc, resume thread, right? And it's the same functions that he's got to call for each of these. So we could just build that out as a string list because the obfuscators he's using aren't going to blow those away. Because if they did, because of the way they're implemented, it would break the functionality, right? Now, he could do something else where he creates another function where he reconstructs those strings and instead, populates them from an obfuscated string, decodes them, encrypts them, whatever, and then puts them back in there as a variable name inside of DLL import. He could do that, but he hasn't. So this is still a pretty good technique for us to use and get a list of some of these other things. The other thing that I was trying to get working, There we go. So the other thing that we can do is we can just come back and take some of the interesting things that we found. So we already found that one. That's a module name. But this guy here, this string value that we've been working with, let's see if I can. Get it to copy here. There we go. Match all words, creatives. So, where is? There we go. That's why I was trying. Okay, now I'm feeling a little better. So you can see that PPSX. That's how he's actually filling out the company, product name, whatever. So it's metadata that he's picked. So we can go ahead and use that, pull these values back together and put them in some context. We're running a little long, so I will just go ahead and take you straight to the cheater, which is this rule here that we wound up writing. And you can see we've got a solid matched rule there, but I'll walk you through what I did real quick and then we'll wrap. So essentially took the meta build values, so for the different assembly name, the custom attributes and the rest of that, and created a build meta section in my variables, and then took the function names that he couldn't successfully obfuscate and put those into a set of functions. Then we use .NET and PE. So PE is DLL, and then the .NET version that we exploited. And the one thing I was unable to find and show you, though it shows up in strings, is the type lib, which that's going to be exclusive to our guy until he watches this video and then blows away his Visual Studio install. But so quite honestly, just those two, .NET version and type lib, pretty decent for being able to follow our guy around the internet right now as he's working. But yeah, this rule should probably burn his dropper for some period of time to come. So anyway, thanks for letting me live work one up in front of you. Trying to write a Yara rule in front of a live audience in 10 minutes was a challenge, and thank you for indulging me while I tried it. So. And that's going to be it. Oh, yeah. I got two things to give away. So the first question, why don't you ever XOR something by the key hex 20? I saw that Tom's hand. Correct. All right, you get your choice. You want a Bash Bunny or the Black Hat Python? The which one? The book. All right, awesome. And then second question, where is our guy JWoww from? Who said Brazil? Brazil, yeah. All righty. Bash Bunny, whoops. All right. All right, awesome. Thank you so much for hanging out. Please, the links on the last slide there, take you to the docs, take you to Florian Ross' awesome Yara tuning paper, and the GitHub repo where these rules are, and the new rule will be shortly. So thanks so much.